So in the first video on hypothesis testing, we talked about step 1 here for hypothesis testing, which is stating the null and alternative hypothesis. So now we're going to continue on, and step 2 I have put in here as the second step because in real life this is where this step would occur. And this step says that the researcher is going to specify a significance level. Okay, that level is going to be the level at which we think the data is convincing. This is specified by the researcher, and it should be done in advance of the next step, which is to gather the data, which is why I wanted to put it in here in our logical order of hypothesis testing steps. In a textbook kind of problem, this information will be supplied as part of the problem. And we're going to talk more about the choice of significance level actually in the next video. But an important note to remember before we go on. So I just said at this point in the process is when the researcher would gather the data. So none of what we're going to talk about fixes bad data. The most fancy statistical algorithms in the world don't fix bad data. So garbage in, garbage out. None of what we're going to talk about really makes any sense if you have bad data. Like if there's confounding factors or selection bias. None of this fixes that kind of thing. So let's go back to the first example that we looked at in the last in-class exercise. And that exercise said, in a standard drug treatment, about 35% of patients experience headaches as a side effect. And a new modification of the drug treatment is tested to see if it reduces the side effect. Now, from that, we set up our null and alternative hypothesis. So now we're going to go on to the next sentence, which in setting up the hypothesis, remember, like we said, just cover that up. If we don't have a crystal ball, we haven't seen the data yet. Okay, so now we're going to look at the data, and the data tells us that in a sample of 75, 20 patients experienced headaches with the modified drug treatment. So what have we been given? So first of all, we have a new symbol here, and that's P with a subscript of 0. And that comes from the null hypothesis. Okay, so that 0 here goes with the 0 in the null hypothesis. So that's P from the null hypothesis, which we sometimes call H naught, like the naught for no. And when that's pronounced out loud, it's called P naught, is what you'll commonly heard it called. It came to my attention some years ago that my students thought I was calling it the peanut, as in peanut butter. Now, I love peanuts, and I eat peanut butter like every single day for breakfast. But this is the peanut, not the peanut. I don't know if I have 20 years worth of former students that think it's called the peanut. But if you ever think I'm saying that, I'm not. I'm saying P not. I'll try to say P from the null hypothesis, but I may slip and call it P naught. So yeah, not the peanut. Our next given, n equals 75. That's our sample size, just like in previous sections. And P hat, in this particular case, they're not giving us a percentage. They give us an actual number, so we have to find the percentage ourselves. So the sample percentage is 20 over 75, which is 0.27. Okay, so our alternative hypothesis, what the researchers were hoping to show, is that the percentage getting side effects was reduced. 0.27 is less than 0.35, so it was reduced in our sample. But we know from the central limit theorem that sample percentages are going to be normally distributed around the true percentage, which equals 0.35 if the null is true. So sample percentages are going to be normally distributed around that 0.35. We got a sample percentage of 0.27. Where does that fall in this normal distribution relative to that 0.35? So our big question is, what is the probability of seeing a sample percentage of 27% just due to random error if the true percentage is 35%? And we have already done these calculations back in the last section on the central limit theorem. So the central limit theorem tells us how to answer this big question. So just like with what we did before, we're going to start by converting that sample percentage to standard units. So the next step is to calculate the test statistic, which is the sample statistic, either the sample mean or sample percentage, converted to standard units, assuming the null hypothesis is true. So in general, the test statistic is going to equal the observed sample statistic minus the hypothesized value of the parameter, so p or mu, divided by the standard error. So for testing hypothesis about population proportions, this is our formula. And notice this is what we've been calculating all along, exactly what we did in the last section for the central limit theorem. So Z is our test statistic, and one little twist on this is that when we calculated Z for our central limit theorem problems, in our denominator we used P, the population proportion. So in this case now for hypothesis testing, we're going to use P from the null in the denominator because we assume that the null is true. So P hat is an estimate, and we're assuming that the null value is true, and that's also written down here with a little star by it. And just one last note on this page, this is all based on the central limit theorem, so our central limit theorem rules hold true. And I see that there's a typo on this page. This should be n times p null is greater than or equal to 5. And n minus that same quantity is also greater than or equal to 5. So this is the same central limit theorem rules that we looked at before. So now plugging our givens into our formula, we have 0.27 minus 0.35 divided by square root of 0.35 times 1 minus square root of 0.35 all over n, which is going to give us minus 1.45. So remember, our big question was, what's the probability of seeing this sample percentage of 0.27 if 0.35 is the true value? That probability is called the p-value, and the definition is p-value is the probability of seeing the sample data or more extreme just due to random error if the null hypothesis is true. So we're going to draw our normal table, and we're here at minus 1.45. And the alternative hypothesis tells us which side to shade on the normal table. So since our alternative said that p was less than 0.35, that means we're going to shade the less than side. Shade less than side because the alternative hypothesis has a less than sign. And the p-value equals this area here. And from the normal table, we can find out that the area on the less than side of negative 1.45 is 0.0735. This tells us there is a 7.35% probability of seeing a sample percentage of 27% just due to random error, or I'm going to say just by chance, in a sample of people taking the original drug. So if we took a sample of 75 people taking the original drug, not the modified one, there would be a 7% chance of seeing a sample percentage of 27%. So with people taking the original drug, we would assume that the true percentage is 35%. So is this convincing evidence? 7%. Well, I mean, it could happen. So the level at which we're convinced or which we think is strong evidence is really something that's determined by the researcher, like in advance, okay? So that's the significance level that we're going to compare the p-value to. And a lot more goes into the choice of the significance level. So for example, like, is this new drug something really expensive, or is the new drug just another use for aspirin? So a lot goes into this that's beyond the calculations that we're doing right here. So common choices for significance levels are 1%, 5%, and 10%. So this is saying this is the point at which the researcher is going to think that the evidence is convincing. When p-values are less than the significance level, the evidence is convincing. In other words, the results are significant. When the p-values are greater than the significance levels, the evidence is not convincing. In other words, the results are not significant. So if the significance level was 1%, 7.35% would be large, not convincing. Likewise, for 5%, 7.35 would still be large, not convincing. But if the significance level was 10%, then 7.35% would be small, or it would be convincing. Which leads us to our next step in the process, which is to make a decision about the null and a conclusion about the alternative hypothesis. This is done by comparing the p-value to the significance level, like we just did on the previous slide. When the p-value is larger than the significance level, okay, that indicates that there's a large probability of seeing those sample results if the null hypothesis is true. So if we start off believing the null hypothesis is true, and there's a large probability of seeing those results if the null hypothesis is true, we have no reason to believe that it's not true. So we're going to keep the null hypothesis when the p-value is larger than the significance level. And our conclusion, if we keep the null hypothesis, our conclusion is that we do not have evidence in favor of the alternative. Or, in other words, the results were not significant. On the other hand, when the p-value is smaller than the significance level, That means there's a small probability of seeing those results if the null hypothesis is true. So that gives us evidence against the null hypothesis. And if we throw out the null, what we're left with is the alternative hypothesis, because we only have these like two choices. We're either going to keep the null or we're going to decide we have evidence in favor of the alternative. So just to summarize is this chart, and it's not that you have to like decide at each one of these like which box to be in. There's only two paths through. Either the p-value is larger than the significance level, in which case you're going to keep the null hypothesis and conclude you do not have evidence in favor of the alternative. Or the p-value is going to be smaller than the significance level, in which case you're going to reject the null hypothesis and conclude you have evidence in favor of the alternative. So there's only two possible paths you can take. So just pick a lane and stay in it. Larger than the significance level tells you keep the null hypothesis, tells you you do not have evidence. Or p-value smaller than the significance level tells you reject the null hypothesis, tells you conclude you do have evidence in favor of the alternative. So on this next page, I want to take a look at how the sample size ends up affecting that p-value. So with the sample size of 75, we had a z-value of negative 1.45 and a p-value of 7.35%. And that was at the 5% level. That's a large p-value, so you would keep the null hypothesis and conclude you do not have evidence that the new drug reduces the side effect. What if the sample size instead was 100? How would that affect the calculations? So if you still had a sample percentage of 27%, the numerator would be unchanged, and in the denominator, however, you would have 100 in place of the 75, which would give you a z-value of minus 1.68 when you plug it in the calculator, and finding a p-value with negative 1.68 instead of negative 1.45. The area, when we look that up in the normal table, is going to be 0.0465. And if we're using the significance level of 5% as our cutoff for what's convincing, this is now smaller than 5%, which would mean you do think the evidence is convincing, and you would reject the null hypothesis and conclude that you do have evidence that the new drug reduces side effects. So at this point, you should pause the video and take a couple of minutes to try and find these p-values for sample size of 200 and 600 on your own. Okay, so here are the answers so you can check your work. For n is 200, z is negative 2.37, p-value of 0.0089, and again, so that's a small p-value. Reject the null and conclude you do have evidence. And with 600, that bumps z up to minus 4.11 and a p-value of 0.000. So same, smaller than 5%. Same conclusion. So how does changing the sample size affect the p-value? As the sample size increases, the p-value decreases if the sample percentage stays the same. So if you think about it, like as the sample size increases, that's stronger evidence. You're seeing that result with more people. And so the probability of seeing it is going to go down. Probability of seeing it if the null hypothesis is true is going to go down. And the next question, which decisions above would change if we used a significance level of 1% instead of 5%? Well, if we had 1%, 0.0465 here in B would be large compared to 0.01. So you would keep the null and conclude that you do not have evidence that the new drug reduces side effects. So on page 54, talks about how we would actually calculate p-values if we had a two-sided test. Suppose we wanted to test if the new drug differed in E with regard to the percentage that have headaches as a side effect. So like perhaps this new drug is different in some other way, and they want to check, well, how is it going to affect the headaches? Is it going to increase them or is it going to decrease them? So in that case, you would do a not equal to test. So how does that affect the p-value? Well, if the sample size, so n, and the sample percentage p hat are the same, then z is going to be the same. And the only thing that's going to change is the p-value. So for example, if we had a less than test and z was -2, our p-value would be that area in this sketch right here. A not equal to test says we're going to test if it's that different in either direction. So the probability that it's going to be a sample result will be that far away on the less than side, or that same distance away on the positive side. So what's going to happen with the p-value is, as you can see in this picture, it's symmetric, as we know the normal distribution is. So the area shaded here for the not equal to test, when z is -2, is just going to be double what it is for the less than test. And likewise, if you had a positive z from your test with a one-sided greater than test, that would be your p-value. A not equal to test is going to look for the probability of being that distance away, either on the positive side or that same distance away on the negative side. So again, you're going to take the p-value that you would get from a one-sided test and double it. So in general, find the tail area, the small piece, and double it. Now, if you double the wrong piece, you're going to get a p-value greater than 1. Probabilities cannot be greater than 1, so p-values cannot be greater than 1. If that happens, you doubled the wrong piece. So just remember that probabilities and therefore p-values, which are probabilities, cannot be greater than 1. Okay, so let's look at a different example. And in this example, we have a school board decides that if more than 60% of high school drivers in the district report that they often drive while drowsy, they're going to move the start time from 7:30 to 8. And in a sample of 200 students, 71% report they often drive while drowsy. Test the appropriate hypothesis at 5%, at the 5% significance level. So what is the null and alternative hypothesis? Okay, so first of all, we're testing percentages. So we can put our parameter of p in our hypothesis. The null hypothesis always has an equal sign in it. And if we covered up the data, so like if you cover up the part in a sample of 200 students, like if you covered this up, what would you be left with? Yeah, cover all that up. So what you'd be left with is the 60%. Okay, so that's our current value, or the value they're going to test against. And put that in both of our hypotheses. And now all we need is a direction in our alternative. And they're going to test and see if more than 60% of the high school students report driving while feeling drowsy, or often driving while feeling drowsy. So that means since it's a more than, we're going to use a greater than test. Our givens are, okay, so P from the null hypothesis is 0.6, coming from right there. Our sample percentage is 0.71, coming from that sample of 200. Our sample size is 200, and when we fill all that into our formula, we have 0.71 minus 0.60 divided by 0.60 times 1 minus 0.60 all over the sample size, square root that, which is 3.175, or rounding to 2 decimal places, which we need to do to look it up in the table, 3.18. So we're out here at 3.18. Our p-value is the area on the greater than side. So when we look up 3.18 in our table, we're going to find an area of 0.9993, because the table always gives us the less than side, which means our area over here is 1 minus that, which is 0.0007. So, like way less than 1%. So this is a small p-value. Okay. It's less than the significance level of 5% from up here, which puts us on the path to reject the null hypothesis and conclude there is evidence that more than 60% of the high school students often drive while drowsy. So before we go on, let's actually talk a little bit more about what that probability or that p-value meant. What probability is that measuring? So remember our definition for the p-value. It's the probability of seeing the sample results, or more extreme, if the null hypothesis is true. So you can think of this as a giant fill-in-the-blank sentence, or a long fill-in-the-blank sentence. So the p-value, so there's a 0.07% probability of seeing a sample percentage of, and our sample percentage was 71%. And we were doing a greater than test. Okay, so we'd say or more. Less if it was a less than test, or more extreme if it was a not equal to. If the null hypothesis is true, and the null hypothesis says the true percentage is 60%. So at this point, you should do in-class exercise number 20 on pages 59 and 60. So at this point, I would suggest pausing the video and doing the hypotheses. So the part A for both of those problems, the one on page 59 and the one on page 60. So pause the video, do that, and then check back to make sure that you have the hypotheses correct before you proceed with parts B through G, because if the hypotheses aren't correct, then everything else is going to be incorrect. So make sure that we get everybody off on the right foot. So pause the video. So in the first problem on page 59, the null hypothesis is going to be coming from a nationwide, the percent of adults who have visited a dentist in the last year is 69.7, so 0.697%. And let's suppose, remember, we're going to cover up the sample data, so we're not looking at that sentence that says in a sample of 8,107 main adults. So covering that up, and what it says is that they're going to test to see if the percentage is lower than the national average. Okay, so this is coming from here. Okay, so now go ahead and finish that problem. And the hypothesis is a little bit trickier in this one. It says a survey of 140 randomly selected students from 9 business courses was taken to determine instructor behaviors that contribute to academic success. One of those instructor behaviors was encourage team or group work. A total of 84 students rated this as important. But remember, we can't really look at that right now unless we have a crystal ball. We don't know what happened in the sample. Okay, so it goes on to say, could the researchers conclude that a majority of students feel that group work contributes to academic success? Okay, so our directional word here is majority. And a majority means more than half, or in other words, we're going to test if P equals 0.5 versus that P is greater than 0.5. So this is similar to the candidate example that we talked about in class, and also the ESP example. So sometimes you have to deduce from the problem what the hypotheses are, and the number is not always exactly mentioned, particularly when it's 50%. So now finish these problems, and we will talk about them in the next video. And so that's it for tonight.